but I'd like to introduce you to Dr. Craig Butt. He is our marketing manager in the applied markets here. He's Canadian, started his journey professionally and personally in Canada, went to Duke University and a few other established institutions, and then he came back to SCIEX to basically participate in what we have in terms of the world of PFAS. So without further ado, I'll leave it over for Craig to give you a brief history of PFAS and how that's relevant and how that's going to shape the entire conversation for the rest of today. So take it away, Craig.
Terrific. Thanks a lot, Francis, and thanks everybody for joining us all across the globe. This will be a very brief history of PFAS, really to kind of set the tone and get us warmed up for our content today from our internal speakers and then our external speakers tomorrow. Those that have some familiarity with PFAS will know that there's a lot that I won't be discussing and a lot I'll kind of be glossing over. And that's really for the sake of time. I think to do a thorough investigation of the history of PFAS, we would need several hours and perhaps an entire symposium itself. So if you can move to the next slide. So really for most of us, and certainly me, our really exposure to PFAS started back over 20 years ago now, right? In 2001, two papers were published that really kind of started the scientific journey for most folks. And, the first one from Hansen on the right-hand side showing the work of PFAS in human serum. This was from a group of American blood donors showing that PFAS had reached the general public. And then on the left-hand side in wildlife from 𝗣𝗙𝗫 and Keenan came out later that year, showing not only was PFAS getting into wildlife and bioaccumulating, but it was moving pretty far up the food chain and biomagnifying. And in fact, wildlife from remote parts of the world, such as the polar regions and the Canadian Arctic, in the middle of the Pacific, were being exposed and accumulating PFAS. So, these two crucial studies really started the journey for a lot of folks. Next slide. However, as I think most of us are aware, PFAS did not start in 2001. Back in the late 30s, the development of PTFE, later commercialized with the trade name Teflon, and then in the 50s, when 3M started manufacturing PFAS in their Minnesota plant using a process known as electrochemical fluorination. Soon thereafter, as we are aware, DuPont began using the PFOA that 3M made in some of its manufacturing processes, using a process known as telomerization. And then in the 60s, the development of the 𝗣𝗙𝗏𝗏 firefighting foams to combat petroleum-based fires began. And of course, this is significant because 𝗣𝗙𝗏𝗏 can be a dominant form of some water contamination. And then in the late 60s, we began to get hints that perhaps PFAS were starting to accumulate in human blood. Now, the technology was not quite available to really confirm what those PFAS were, but I think that's perhaps was the first indication to the scientific community that PFAS were building up in human blood. So go to the next slide. And I'll say too as well, I mean, there's a lot of history that we now know and has been well documented. But of course, again, that would take many slides to thoroughly explain. So I'm just kind of hitting on what I think are the salient parts. And as I mentioned in the last slide, really the early work by 𝗍𝗃, we didn't have the technology, the analytical technology to confirm what those PFAS chemicals were on a compound-specific basis. And it really wasn't until the development of electrospray ionization in the 80s by John Fenn. And of course, we kind of take it for granted now that we have this analytical technique. But back in those days, it was quite novel. And in fact, this is such a groundbreaking development that he received the Nobel Prize for it, and really has made possible the analysis of a lot of chemicals that otherwise we wouldn't be able to measure. And as I showed on the first slide, the early 2000s really were those introductory original papers showing that PFAS was accumulating in human blood and wildlife. And not only that, but moving quite far away from its original point of manufacture. And, again, when you think back to the time, there was a lot of focus on the persistent organochlorine, such as the pesticides, DDT, as well as PCBs and dioxins, but then also the brominated compounds, such as the brominated flame retardants. And so this really was a major shift away from those other organohalogen species. And, amongst that was the fact that we needed LC tandem mass spec to see a lot of them, not GCMS as, the older organochlorine and bromine compounds needed. So, what this meant is, for us as environmental chemists, is that an entire new skill set was needed to learn how to analyze these with high data quality. So, from there, as we, quite immature in terms of our analytical techniques and our knowledge, the mid 2000s really saw this explosion in terms of scientific evolution into measuring PFAS, from improving our analytical methods. Wellington Labs, when they started making their mass labeled standards as well as native standards, we saw another leap forward in terms of data quality. And some of the questions at the time that we had are pretty fundamental. And again, we kind of take it for granted that we've answered a lot of these questions or addressed them pretty thoroughly. What PFAS are being used out there in our commercial products? What commercial products are they in? And, we continue to find surprises even today. Lots of questions in terms of fate and transport. Really, PFAS didn't fit the typical model for something that should travel far away to remote regions. And so we had lots of questions about how they got to polar regions and how they biomagnified up the food web, and why are polar bears some of the most contaminated animals on the planet. And then as we kind of dove in, we started asking the questions about the PFAS precursors. I think it was understood that the PFAS we're measuring in wildlife and blood isn't quite what is being used. So there's lots of questions about those precursors. Go to the next slide, please. So those are some of the kind of the early to questions and struggles that we had. I show this because this is back from 2004. A group of scientists at the time got together and really kind of addressed what some of the limitations were in terms of good PFAS data quality. And of course, without that quality, you can't make conclusions about their fate and their transport and toxicology. So just a couple of things that highlighted at the time, the poor quality of standards and really unknown purity in some aspects shown in the middle. And then in the kind of top right-hand side, showing the fact that there were some biological interferences for PFAS and the hexane sulfonic acid. We now understand what those are, and we have techniques to minimize those interferences. But again, at the time in the early 2000s, these were issues that scientists were first starting to understand, and we needed to move past. So if we go to the next slide. So just a little bit in terms of the PFAS regulations. And again, I know other speakers will touch on this much more thoroughly than I can. And again, this is just kind of a quick snapshot of some of the more important ones along the way. Certainly we hear about some developments in the last year and months, but it's important to recognize that actually back in 2006, right, June 2006, Canada took the first efforts to ban PFAS by banning the import and manufacture of four fluorotelomers. And that was important because they applied a little bit of the precautionary principle, to ban things that could break down to some of these carboxylic acids that were accumulating. The PFOA stewardship program was quite an accomplishment in this agreement between the U.S. government and the major manufacturers to actually phase out PFOA, the C8 carboxylic acid, and its precursors, and that includes the longer chain compounds by 2015. So a monumental agreement there between industry and government. On an international side, 2009, seeing that PFAS declared a persistent organic pollutant in the Stockholm Convention. And then, of course, in the 2000s, right, last year, the big one with the EPA announcing its new health advisory levels, the so-called 4 ppq for PFOA, for its guidelines as a health advisory level. And then I think as well, shown on the bottom left-hand side, the EPA's 3-year testing roadmap, I think, is an important document in terms of plotting out a strategy of how to deal with PFAS and looking at the entire PFAS life cycle. So go to the next slide, please. And then, of course, the most recent thing, right, announced last month, is the proposal from the EU to ban PFAS in terms of its production, use, and sale of approximately 10,000 different compounds. We're still trying to understand what exactly this means. This is still in the draft stage, open for comment, but certainly this has the ability to make a large impact, not just in the EU, but also globally. And I kind of show that by one headline on the right-hand side, talking about the staggering impact. Now it mentions the United States, but of course, we live in a global environment, so this will impact countries all over the world. Okay, next slide. All right, so we've touched on some of the early analytical challenges, and I just want to come back to that. And what you'll notice is throughout my presentation is I'm going to be touching on kind of how things were back in the early days, and then kind of jump forward to where we are today. In the early days, we had a lot of development and struggles in terms of measuring PFAS and looking at some individual compounds. But really, we've made a tremendous jump forward in those 22 years. And our modern analytical techniques and certainly our instrumentation has pushed our limits lower and lower, allowing us to get down to those 4 ppq in drinking water levels. But with the struggle to measure all of the PFAS that might be in the environment, we've moved beyond those 3 or 4 compounds that we used to measure in the early days, and trying to quantify a total PFAS. Of course, it's very difficult to do, and there's a few techniques that have been used to try to measure the total PFAS burden. High-res instruments like the one that I've shown in the bottom right, the 7600 QTOF, are very good for doing non-target analysis and then screening. I think in the early 2010s, the development of the total oxidizable precursor, the TOP assay, to look at really what potential there was for precursors to form the perfluorinated acids was a big step forward. And I'll show some examples later on as well. Good. Next slide. And then in terms of another technique to screen for total PFAS, the development of a total organic fluorine or total fluorine methods kind of in the late 2000s, and then its applications in terms of measuring wildlife and humans and commercial products are important. And this is a good one here that I've shown from Schultz, looking at food packaging. And what you can see on the right-hand side is we have our targeted analysis for what PFAS are there. And then on the right-hand side, we have our total fluorine measurements in the kind of that white bar. And if you look at the red lettering there, that is the amount that the researchers were able to quantify. And you'll notice it's all less than 0.1%. So what does that mean? It means that our targeted techniques are doing a very poor job of understanding the total PFAS that are in these food package samples. So a good example of using total fluorine to try to get at a total burden of PFAS in a commercial product. Go to the next slide. And then here, the particle-induced gamma ray emission, the PFAS, so-called PFAS technique. This is also a good technique to try to understand the total fluorine content. And here I show it used for cosmetic samples. And the same kind of story here is that our targeted techniques actually do a pretty poor example here of quantifying what's in this case, cosmetic sample. Okay, next slide. All right, so I'm just going to touch on a little bit about PFAS sources and where they come from. Next slide. So again, back in the early 2000s, we had a lot of questions about what PFAS were in commercial products and which really what those were. And here's a good example looking at some commercial products and looking at the volatile precursors. Again, and this is kind of getting to the question of the role of precursors in the PFAS life cycle. So, this was pretty groundbreaking at the time in 2006 to show that not only there were volatile precursors in commercial products purchased off the shelf, but these could then escape into the atmosphere. And so we'll go to the next slide. Then we fast forward really to modern times, right? And we've moved beyond that and using total fluorine to try to understand not just the specific compounds that are there, but a true burden of all the diverse PFAS that are in a product. So we have our screening technique for total fluorine, but then you can see here using a QTOF technique, quantifying really up to about 90 different PFAS. And you'll notice here, the third bullet point, there's a lot more classes of PFAS that we're aware of that have their own unique fates, and that we can quantify. So again, kind of a leap forward from the early 2000s. So can we jump forward to the next slide, please? Okay. So early awareness of PFAS, right, and 𝗣𝗙𝗃. The paper from 2001, which used both a combination of LC mass spec as well as a fluorine NMR. They were able to measure PFAS as resulting from a large release near an airport in Toronto. But you'll notice, they only quantified 3 PFAS, PFOS, the hexane sulfonic acid, and PFOA, which, that was great at the time, but we now know that was a pretty limited understanding. So if we can go to the next slide. And then as developments, both in terms of technology, but also the research efforts, we're able to use some QTOF techniques and other high resolution instrumentation to actually understand the fact that an 𝗣𝗙𝗃 mixture, firefighting foam mixture, is very, very complex and very diverse. And this is just an example of some of the different diversity of PFAS that they were able to measure in the firefighting foam. And next slide. And then kind of jump forward again to modern times, work from 𝗪𝗪 out of Harvard, showing that in fact, even with our good targeted techniques in understanding of some of the diversity of 𝗣𝗙𝗃, we're doing a still very poor job. And if you look at that middle slide or middle panel, panel B, you could see that their targeted efforts really, accounted for about less than 1% of the total PFAS that was in there. And then also you see a nice use of the top assay to oxidize those precursors to try to get an assessment as to what the total PFAS burden could be in those commercial mixtures. Okay, next slide. All right, so we'll kind of jump ahead to fate and transport here and looking at the role of precursors. Yeah. So again, we kind of take for granted the fact that we know PFAS and these precursors are in the atmosphere. But again, back in the day, these sorts of developments, both in terms of the analytical techniques and then the field work to show that they were in the outdoor ambient atmosphere, was pretty novel, and I can say somewhat controversial at the time as well. So here from the early 2000s, the original work from John Martin in 2002, showing that precursors were definitely in the atmosphere, and could be globally distributed. So go to the next slide. Jump forward to modern times here. This is some of the atmospheric work that 𝗀𝗏 Young will touch on tomorrow. But we now know that, for some of these PFAS, particularly these ultra short chain compounds, it may not be the traditional precursors that we think of, right? And these may come from some of the CFC replacements, that are in play now due to things like the international treaty, the Montreal Protocol. So I think this is kind of a really good example where we took those initial measurements, we've advanced it so that we're now starting to understand how PFAS are moving around in the environment, and then how they're responding to changes in productions, and here building up in this case in polar ice caps. All right, next slide. And then this is from the GAPS network, the Global Atmospheric Passive Sampling Network, spearheaded by Tom Harner. And this is an amazing network of passive samplers that cover the globe, but also cover different site uses. Here, polar, urban, rural, or background. And this allows us to get great snapshots of what's going on around the world, but also to see trends in different, let's say, site usage. So a great way to understand, these PFAS compounds as well as the precursors. Okay, next slide. All right, moving on now to aquatic environment and biomagnification. Next slide. So I showed you the first slide from 𝗣𝗿𝗁 and Canaan with PFAS that had been detected in wildlife throughout the world, and soon thereafter we gained a greater understanding of which PFAS were biomagnifying, shown here on the right hand side, and then you can see we've moved beyond, in this case, just PFAS and PFOA to look at other longer chain carboxylic acids. And then work that was done in the mid 2000s, looking at the different components of the food web, and certainly seeing this biomagnification moving up the trophic food webs. The aquatic food webs were the best understood at the time, but certainly we see also trends in the terrestrial food webs. So next slide. And we took those, right, and we've moved again, evolved from those early days to start looking at things in a non-target way, right? And so increasing our understanding of the burden of PFAS in animals such as these beluga whales from the St. Lawrence River estuary in Canada. And what's interesting about it is, as our production of PFAS has changed through time, we see some of the older chemicals starting to drop off in recent years, whereas some of the newer compounds are increasing. I show here the figure from the paper, both looking at the so-called legacy PFAS as well as the novel PFAS. So, kind of a great use here of how our modern analytical techniques can improve our understanding and have really pushed it beyond those initial studies from 𝗣𝗙𝗎 and 𝗀𝗏 in 2001. Okay, next slide. All right. So as we kind of wrap up with this and talk about the history and of PFAS, a lot of where we've come is we've moved beyond the initial measurements in different environmental matrices, and we've understood how a lot of these different life cycle components are tied together. And that's, you'll hear a lot about that tomorrow with our external speakers. So next slide. And then, of course, this is a great session that we've got over the next couple days. Back in the 2005, I was lucky to be part of the organizing committee for the first Fluoros meeting, which was really the first global meeting on PFAS. And that has continued to evolve through other meetings, 2015 and 2021, and then this year at the end of August in Germany for Fluoros 2023. It's always impressive to see the leaps in PFAS research as we go from meeting to meeting. All right, next slide. So just to summarize, of course, PFAS are complex, right? Our understanding of just a few PFAS in humans and wildlife has grown exponentially. Needless to say, regulations are increasing, and they're moving beyond just drinking water matrices into things like consumer products and others. Knowledge will continue to expand in terms of understanding how many true PFAS there are, depending on how you quantify it, but then what those are and what their fate is. Precursors, even the existence of precursors back in the day was somewhat controversial, but now we're gaining an understanding of how they are influencing how the terminal PFAS, such as the carboxylates and sulfonic acids, can move around the globe and build up in humans and wildlife. And then, of course, a lot of this is really driven by these improvements in analytical techniques. Our targeted techniques are getting better and better in terms of measuring lower levels, but also our non-targeted and unknown screening techniques are getting better, moving towards our end goal of quantifying total PFAS. And with that, I thank you very much. Again, this was a very quick summary of the history of PFAS.